Hi all, Adit here. We will continue our topic of limit to one-sided limits and continuity in this video. In the previous discussion of limit, we just say we approach C, but in here in one-sided limits, we will specify from where we will approach C. So if we want to approach C from the left, we will say x to C minus, and if we want to approach C from the right, we will say x to C plus. So here is an example. This is a piecewise function with definition change happen in x equals to 2. So we want to evaluate limit x to 2 from the left and limit x to 2 from the right. What it means to approach 2 from the left is we get close enough to 2 but still less than 2. So in this case, because it is less than 2, we will use the function 1 minus x squared. And that's why we get the limit of x to 2 from the left from this function is minus 3. With a similar reasoning, we will also get limit x to 2 from the right from this function is 5, because we use the function 2x plus 1. We can see that the limit x from the left is minus 3 and limit x from the right is 5. So what happened to the limit itself? Limit x to 2, not from the left and not from the right. We say that the limit doesn't exist, as we can see in this yellow box. So for the limit to exist, the limit from the left and limit from the right need to be coincide. Now try to find the limit x to 2 from x plus 1 over x minus 2. Let's take a look at another example. This time it is in illustration form, so maybe we can see more clearly. So this is the graph of a function f, let's say it's f, and we want to see whether limit x to 1 of this function exists or not. Just from a glance, we can see that the limit x to 1 from the left is 0, while limit x to 1 from the right is 1. The value of the function itself is 1, although it is irrelevant. So limit x to 1 from this function does not exist. While if x equals to 2, limit x to 2 of this function does exist, and they are 1, while the value of the function in 2 is 2. Now if x equals to 3, not only the limit does exist, the value of f3 is also equals to the limit. And here is an example that's totally irrelevant to this course, but I'll give it anyway. So this is an example where the limit doesn't exist because they're too squiggly, so we cannot pinpoint exactly what's the value of a function near that point, in this case near 0. Let's move on to the next topic of this video, which is continuity. So a continuous function is a function which the graph can be drawn without the pen leaving the paper. This is an intuitive definition of continuous function. We will define it more mathematically in the next few slides. But first, we will take a look at the different kinds of hole at x equals to c. On the left, we will see that there's a hole in C where FC is not defined, while in the middle, there's a hole at C but with FC is defined, although it is different to the limit. While on the far right, both limits are infinite and the FC itself is not defined. As for but the second, we will take a look at a few gaps at x equals to c. So there are only two kinds of gaps. The first one is a finite gap, which means both left limit and right limit are finite, although they are different. And the second one is infinite gap. They can be both infinite or only one of them is infinite, but they are still called infinite gap. So for the function to have no holes or gaps, we will now define continue property mathematically, and here they are. There are three things that we need to check to see whether f is continuous or not. The first one is fc must be defined. Second one, the limit must exist. And the third one, they are both coincide. If one of them is not fulfilled, then we call f is discontinuous at c. Now let's go back to our example. At x equals to 1, because the left limit is not equal to the right limit, then the limit doesn't exist. So it is discontinuous at x equals to 1. And for x equals to 2, because the limit and the value of the function are not equal, then they are discontinuous. While at x equals to 3, both the limit and the value are equal, so they are continuous at x equals to 3. Let's go visit our best friends, polynomials and rational functions. Now if we remember correctly, to determine its limit, both polynomials and rational functions, we can just evaluate the value of the functions in C. So because of that, they are continuous whenever they are defined. It is another nice property of polynomials and rational functions. In the next few slides, there are few problems for you to work on. So get on it. And finally, this is the last topic in this video, continuity on an interval. So if we want to check whether f is continuous on an open interval AB, then we have to check whether it is continuous at every point C between A and B. If we want to check whether a function f is continuous in a closed interval from A to B, then we have to check whether it is continuous in an open interval AB and whether it is left continuous at B and right continuous at A. And of course, you can ask for help from our best friends, polynomials and rational functions. And here's an exercise for you. And this is the end. So thank you and see you in the next topic. Maybe. I have to check on that.